So, good morning, students. So, today I will discuss this reciprocity theorem. This theorem is applicable on telecommunication network because some of the students from us are from this branch electronics and communication engineering. So, that's why I will just give more attention for that students towards this theorem. This is just take one example. Let us say I am taking one example of the any of the whether wireless or wired network. Let us say this is your mobile one, right? And this is your mobile two, right? One is I am taking mobile one and mobile two, M1 and M2, and let us say this will be sending some signal and this will receiving some signal, right? I am speaking and you are listening. M1 is, let us suppose, myself, and M2 is the students, right? So what will happen if I am sending some signal, that means I am speaking, then after that, that signal will be converted into the form of electrical signal, and then that will be received at the receiving end, and then at the receiving end, it will be again converted into the some voice signal, right? So two conversions are there. I think you must aware with that transducer. Transducer is a device which will convert non-electrical signal into electrical signal. Fine. So here at the sending end, I am speaking, then that voice will be converted into the form of some electrical wave or electromagnetic waves. Then after that, this will be just move through a space, and then after some modification or some modulation, you may say it will be received at the receiving end, right? Then that electromagnetic waves will be again converted into the form of voice signal, right? So this is the one part. M1, that means mobile one will sending the signal and M2 is receiving the signal, right? Now if same thing will be repeated by M2, same thing will be repeated by M2. That means now M2 will speak at the same decibel, right? At the same decibel, and that means it will just send some signal into the form of electromagnetic waves towards M1, and if M1 again receive the same signal, right? If M1 again receive the same signal, then this particular network, this network is known as reciprocal network. Reciprocal network. Reciprocal means whether M1, if M1 sends the signal, M2 receive it. If M2 sends the signal, M1 receive it at the same value, right? At the same value. Then this network is said to be reciprocal, right? This network is said to be reciprocal, and right, and reciprocity theorem is applicable on this network. In this case, this is only the theorem in which there is no, that means load resistance is given to you. In all the other theorem, whether that will be Thevenin theorem or Norton theorem, right, superposition, maximum power, in all the theorem, what will happen? There is one load resistance, and we will have to calculate current or voltage drop or power loss in that load resistance, right? But Reciprocity theorem is the only theorem in which there is no load resistance. In case of the reciprocity theorem, the question is whether reciprocity theorem is applicable on the given network or it is not applicable on the given network. Right? So what will happen in this particular case? We will have to select the load branch. You may take any resistance as the load branch. Let us say if I am talking about this particular case, in this case there are 4 resistances. You may take any resistance as a load resistance, and then we will have to prove whether reciprocity theorem is applicable on the given network or not. Right? So the thing is, important thing is, if this one signal is sending from the sending end and it will be received at the receiving end, like in this case, sending from the sending end and receiving at the M2, and if the same, let us take, I am saying that here some voltage source will be connected across M1, some voltage source will be connected, this will send a signal, right? And here some current will be obtained, right? Here some current will be obtained, and if I am just placing, let us suppose I am taking here a V is equal to 2 volt, some 2 volt source will be connected here, in between whatsoever is the network, here across it, if I am getting 1 ampere of the current, right? If in case across M1 I am connecting the voltage source of 2 volt and receive just M2 branch drawing current of 1 ampere. Now what to do? In second case, just short circuit the voltage source placed here and now connect that voltage source across this point, across M2 branch, right? Connect that voltage source which will be removed from here at M2 branch, right? And if now again after solving that, solving all the network, you will get at M1 again current is 1 ampere. Then this network is said to be reciprocal network, and this network is said to be reciprocal network, and reciprocity theorem is applicable on the given network, right? This is the basically practical application of the reciprocity theorem. Reciprocity theorem is applicable on the telecommunication network, right? In case of the telecommunication network, this reciprocity theorem is applicable, right? Is it clear? So from this, now let us take this network. Let us take this network for the just proof of the reciprocity theorem. For the proof of the reciprocity theorem, I am just considering this network. I had already told it to you. In case of the reciprocity theorem, there is no load resistance. So you may select any branch. You may select any branch as a load resistance, either R1 or, because in V1 branch all R1 is connected, so I am not considering that R1 as a load resistance. You may take R2, R3 or R4, R2, R3 or R4 as a load resistance, right? You may consider any of these as a load resistance, fine. So I am just considering this R4 is the load resistance. You may take any, again I am repeating, you in case of the reciprocity theorem, there is no load resistance is given to you. The question is whether reciprocity theorem is applicable on the network or not, fine. So you will have to select the load branch. So for this particular case, I am considering this R4 as a load resistance. Now, what is your first step? Step 1 is select any of the load branch. Select any of load branch, right? So I am taking this as a load branch. Step 2, calculate current in the load branch, current in the load branch, right? So I want to calculate current here. So for that, calculate the R equivalent across V1, R equivalent across V1. So this will be this R3 and R4 are in parallel. So that means it will become R3 plus R4. This combination is in parallel with R2. This combination is in parallel with R2, and this total combination is in series with R1. Is in series with R1. Again, I am repeating. At whatsoever point we want to calculate the R equivalent, try to start from the second side, because I think you are in the presently you are in the just starting of your electrical engineering or electronics engineering. So in this particular case, in this particular class, you must capable to understand what is the series connection, what is the parallel connection, what are the star type connection, what are the delta type connection. In any of the complex network, you must capable to identify what is the R equivalent of the network, and this is only by practice, right? If I want to calculate R equivalent across these two terminal, start from the other end, right? So this is the other end. Here you may say R3 and R4 are in series. In this this series combination is in parallel with R2, and this complete combination is in series with R1, right? So this is your R equivalent. Now in term of relation, this will be R3 plus R4 into R2 divided by R2 plus R3 plus R4 plus R1. This is your value of the R equivalent across this voltage source terminal, right? Now after this, total current supplied by the voltage source, that will be given by I1, and here in the load branch I am taking it as IL dash, right? I want to calculate IL dash. So before calculating IL dash, must calculate I1. So I1 is equal to V1 divided by R equivalent, right? So you may substitute the value of R equivalent here. This will become V1 divided by R3 plus R4 into R2 divided by R2 plus R3 plus R4, right? So this is your value of the I1, fine. Now from this I1, by using the current division method, you may calculate IL dash. So IL dash is equal to, I want to calculate the current in this branch, opposite branch is R2. So total current, that is I1 into opposite resistance, that is R2 divided by R2 plus R3 plus R4, right? So this is your load current when this is your load current in the branch R4 This is your load current in the branch R4 when in the branch R4 when this voltage source is placed in the branch of R1, right? This is your first reference equation. First reference equation is IL dash is equal to I1 into R2 upon R2 plus R3 plus R4, right? Now, next step. In next step, let's consider the next step. In step 3, now what to do? Remove the voltage source from branch R1. Remove the voltage source from branch R1, right? What to do here? And short circuit at terminal, then place voltage source in branch which is assumed to be as load branch, which is assumed to be as load branch. So what to do here? Across this point, this I am writing here, IL dash equal to I1 into R2 plus R3 plus R4. This is your equation number 1. Now I am just going to count it. Now, to do here, as per the step 3, remove the voltage source from the branch R. Wherever that voltage source from that branch, right?
Sir, not able to hear you.
Right. Now, what to do? Just remove the voltage source. Remove the voltage source from the branch where it is placed in first case and place short circuit there, and then after that place the voltage source in the branch where current has been calculated, right? So I'm just redrawing that. V1, that terminal will be short circuit, R1, then R2, R3, R4, and here that voltage source will be placed, V1. That voltage source will be removed from this point, short circuit is applied here, and voltage source is placed at this terminal because here we calculated the current, right? After applying the step 3, this is your network, fine. Then after that, this next is apply basics and calculate the current in the branch from where voltage source is being removed, right? That means now I want to calculate the current in this branch. Now this is your load resistance. In first case, R4 is the load resistance. In this case, R1 is the load resistance. Why? Because voltage source is placed in the R1 branch, right? Now I want to calculate the current in this branch. So IL double dash is required to be calculated. So for IL double dash, here I may calculate I3, right? For I3, calculate. Next step, step 4, calculate current, calculate current in branch from where voltage source has been removed. Voltage source has been removed, right? So here for this, calculate the R equivalent dash. Let us suppose R equivalent dash here across the V1 terminal. R equivalent dash, that is equal to, see here, I want to calculate R equivalent here. So R1 is in parallel with R2, and this combination is in series with R3 and R4 combination. R3 and R4 are in series, and this combination is in parallel. This parallel combination is placed in series with this. So R equivalent dash, that is equal to, here this will become R1 R2 upon R1 plus R2 plus R3 plus R4, right? So this is your R equivalent dash, right? This is your R equivalent dash. Then after this, calculate the total current supplied by the voltage source now. So that will become, this is your R equivalent dash. R equivalent dash is equal to R1 R2 divided by R1 plus R2 plus R3 plus R4. So this is your R equivalent dash, that is the voltage source R equivalent, total equivalent resistance across the voltage source terminal, right? So here it is I3, total current supplied by the voltage source now, that will be I3. I3 is equal to V1 upon R equivalent dash. Fine. So substitute the value of R equivalent dash here. V1 upon R1 R2 divided by R1 plus R2 plus R3 plus R4. Fine. So this is your value of this total current supplied by voltage source. Now I want to calculate the current in branch R1, right? I want to calculate the current in the branch R1. So again, use the current division method. IL double dash, that is equal to total current, that is I3 from this into opposite resistance R2 divided by R2 plus R3, right? IL double dash, that is equal to I3 into R2 upon R2 plus R3, right? So this is your equation 1 and this is your equation 2, right? So if equation 1 is equal to equation 2, if equation 1 is equal to equation 2, right, then that means value of the current in both of the cases is equal. IL dash is equal to IL double dash. Then reciprocity theorem is applicable. Reciprocity theorem is applicable on the given network. Reciprocity theorem is applicable on the given network, right? If in any case IL double dash and IL dash are not equal, if in any case IL double dash and IL dash that are not equal, then in that case, we may say that reciprocity theorem is not applicable on the given network. But if generally in as far as examination point of view, whatsoever problem will come, that in that network it is generally applicable, right? So this is not like that any problem will be given to you and reciprocity is not applicable on that network. Generally it is applicable, right? So here rest depends upon problem to problem. So in this case, if IL dash is equal to IL double dash, then reciprocity theorem is applicable on the given network. Fine. This is the problem. This question gives you one problem that what should be the value of R such that maximum power transfer can take place from the rest of the network to R in this network and obtain the amount of this power. One is you will have to calculate that value of R, and second is you will have to calculate that value of maximum power transfer, right? So R is equal to, we know that for maximum power takes place, maximum power takes place, this RL is equal to R Thevenin. Internal resistance of the source is equal to the load resistance, right? So here RL is equal to R Thevenin. So that means this is your RL. We will have to calculate the R Thevenin for this case, and that is your load resistance. So again, use the same step as that of the Thevenin theorem. Remove the load resistance. So I'm just removing it. So remove the load resistance. Then after that, open circuit all the current sources and short circuit all the voltage sources. This current source will be open circuit. This is your 2 ohm resistance. Then here it will be X and Y. This will be 5 ohm. Here it will be this 10 ohm, and here it will be voltage source, that will be short circuit. So this is your network after open circuit, current source and short circuit voltage source. So by keeping this X and Y at the outer one, this is your X, this is your Y. Again, calculate from X, it will be 2 ohm. Then this 2 ohm here, open circuit, no need to write. Then 5 ohm, and here it will be 10 ohm. Right? So this 5 and 10 are in parallel, and this combination is in series with 2 ohm. So here I want to calculate R equivalent, that is your R Thevenin. Right? So R Thevenin is equal to 5 in parallel with 10, and this combination is in series with 2 ohm. So this will be 5 into 10 divided by 5 plus 10 plus 2. So this will be 50 by 15 plus 2. So that will be 80 upon 15. Right? So R Thevenin is equal to 5.33 ohm. So this is your value of RL. RL is equal to RTH, because in case of your maximum power transfer theorem, if load resistance is equal to, if load resistance is equal to internal resistance of the source, then maximum the power transfer takes place. Fine. So here this is the amount of RL, because this is your value of the RTH, R Thevenin, right? Now, what is the amount of the maximum power? VTH square. P maximum is equal to VTH square upon 4RL, right? That means I need the value of VTH. I require the value of VTH, right? So here again consider this network. In this network, if you see here, this current source and resistance are in parallel. Whether you may convert, there it will be terminal X and Y. Either you may convert that into the this voltage source, or you may consider as such. So here I want to calculate Vx, then here it will be Vy, then Vx minus Vy or Vy minus Vx, that is the required value of VOC or VTH, right? So for Vx, I am applying, let us suppose this is your node A, at node A, apply at node A, apply nodal analysis or ACL, right? So here that means 5 ampere is incoming, and here it will be again I is equal to 5 ampere. Okay. We get I through 2 ohm resistance. I through 2 ohm resistance is 5 ampere, right? So that means Vx is equal to I into R. Vx is equal to I into R. I is 5, R is 2. So Vx is equal to 10 volt. Vx is equal to 10 volt. Now I want to calculate Vy. I want to calculate Vy. So for Vy, this is another side of the network. Here some voltage source will be given to you. Voltage source will be given to you. This is your network. Here I am assuming I1. So in this is your loop 1. In loop 1, apply KVL. In loop 1, apply KVL, right? So when you apply KVL, what you will get, the summation of V is equal to summation of IR. Summation of V is equal to summation of IR. So 24 is equal to I1 into 10 plus I1 into 5, because on the other side there is no current. So 24 is equal to 15 I1. Fine. 15 I1. So from this I1 is equal to 24 by 15. So 9.6. 1.6 is the value of 1.6 ampere. So I1 is equal to 1.6 ampere. Then by using this value, you may calculate here RL. I am just writing here. RL is equal to 5.33 ohms, right? Then I1 is equal to 1.6 ampere. From this, Vy is equal to I1 into 5. I1 into 5, right? So this I1 into 5, 1.6 into 5, that will be 8 volt. Vy is equal to 8 volt. Now this VOC is equal to VTH. I want to calculate open circuit voltage here. I want to calculate open circuit voltage here. That will be simply this. That will represent Thevenin equivalent voltage, right? So this Thevenin equivalent voltage will be either equal to Vx minus Vy or Vy minus Vx, whatsoever is higher. So here Vx is 10 volt, Vy is 8 volt. So this will be Vx minus Vy. So that will be 10 minus 8 is equal to 2 volt. So VOC is equal to 2 volts, right? VOC is equal to V Thevenin. VOC or V Thevenin are the same. So V Thevenin or VOC, that will be equal to 2 volt and RL is equal to 5.33 ohm. Now as per the maximum power transfer theorem, as per maximum power transfer theorem, as per maximum power transfer theorem, power across the load maximum is equal to VTH square divided by 4 RTH or 4 RL. So VTH is equal to 2 volt. So this is equal to 2 square divided by 4 into 5.33. So you may calculate 1 upon 5.33 in watt. Power is V square upon R, V square upon 4 RTH, right? So this will be, you may calculate it. Just a minute, I am just going to calculate it. 1 upon 5.33, 1 upon 5.33, that will be 0.1876. 0.1876, or this may be, this is in watt, but I want to increase the significant bits, so this may be 187.6 milliwatt, right? So power across the load at the condition of maximum power transfer, power across the load at the condition of maximum power transfer, that will be equal to 187.6 milliwatt, right? 127.6 milliwatt by using maximum power transfer theorem. So this is one numerical problem related with maximum power transfer theorem. So this is the end of the lecture. Thank you.